Okay, guys, we learned how to solve differential equations that had a analytical solution. Now let's learn how to solve differential equations in Mathematica that do not have an analytical solution. Again, we learned how to do this in MATLAB, but it can also be useful to know how to do this in Mathematica. Okay, so we're going to look at a 1D projectile again, but instead of throwing balls, we're going to launch a rocket. Okay, so we're going to think about what happens to this object if it doesn't stay close. I'm going to capitalize right here, to the surface of the Earth, and we're going to use the full form of Newton's law of gravity. So instead of just assuming the acceleration of gravity or the force of gravity is constant, we are going to use the expression that is more correct, that says the force of gravity decreases like 1 over r, or distance from the center of the planet squared. Okay, so here G is the universal gravitational constant, M is the mass of the Earth, and Z is going to be the distance from the center of the Earth. Okay, so the difference between what we did before and what we're doing now, before we used for an analytical ODE, we used D-solve. Now we're going to use its cousin for differential equations that we're solving numerically, which is ND-solve, basically numerical differential equation solver. Okay. Just like in MATLAB, second order differential equations are hard to solve directly with numerical methods. There are some methods, but it's much easier to turn them into coupled first order differential equations and solve them together. Okay, so for this one, let's go ahead and do that. We practiced doing that when we learned how to do this in MATLAB. So for this equation here, a second order differential equation, I can break it up into two first order differential equations. The first one tells me that the rate of change of a position z is equal to the velocity. The second one tells me that the rate of change of the velocity is equal to negative gm over z squared, basically the acceleration of my rocket, or the acceleration of gravity. Okay, so very similar to what we did before. And again, there's a lot of text here that I'm just going to leave because you guys can read this if you want later. We're going to go ahead and define, again, a list of equations that we want to put into our differential equation solver to help them solve. In this case, we've got two first order differential equations. And again, notice I am putting double equal signs here. It's more like a condition. This thing is equal to this thing. It's like a logical thing, okay? So the first order of this thing z or the first order derivative of this thing z with respect to time is equal to v. The first order derivative of this thing v with respect to time is equal to all of this. Notice that they are related to one another in some way. Okay, that's in here too. And then I've got my initial conditions, which I can keep them pretty general. So the velocity at time 0 is equal to v naught. The position at time 0 is equal to z naught. Okay, there we go. Needed to declare, again, important thing to do. So now I've got a list of our mathematical relationships that I'm going to put into ND-solve, okay, just right now. All right, so let's go down here. Now, again, I'm solving this numerically, which means I need to get numbers out. There is no analytical solution. So just like if I was doing this in MATLAB, I need to actually give numbers for each of these things, okay? So I have to tell it basically what all of these variables that are not defined are equal to. And I'm going to do this using this slash dot notation again, because I want to keep this in this form so I can easily change what these variables are without having to rewrite all of this, basically. So I'm creating a new test case, and my test case, m is going to be equal to this, which is in, I don't know if I've got the units up here, but kilograms, okay? G is equal to the gravitational constant, okay? So I'm saying we're going to replace G with this value, V naught's going to be replaced with this value, and Z naught's going to be replaced with this value. And this should all be in standard units. Let me put a meter up here. And this is going to be in seconds. Okay, and then I'm going to define some min and max times that I want to solve this on. And then let's look at the syntax for the solution. So ND solve, And then just so I can make sure you guys understand what that is, I'll put this separate up here. I'm going to say, hey, go into this list of equations and make all of these replacements, okay, and then solve that. But now I want you to solve it for, because I've got two first order differential equations to solve, I'm going to get two solutions, okay? And this again is very much like what we did with Runge-Kutta, okay? When in the very last lab that we did. So I'm going to get values out for both the position of this object and its velocity with respect to time. And again, it's going to be evaluated from this minimum time to the maximum time. So I'm going to put this on a separate line, just quick. Let's just do this first, so you can see what we're evaluating here. Oops. So here we can verify, right, what we just did with that slash dot notation is replace in this general form those variables or those constants with numerical values, so I can actually do the solving of it. And then let's just run the ND solve. Okay, whoa, what did I get here? So remember, there is no analytical solution to these particular equations. I can only get a numeric solution. So that's what I'm getting out here. So what this is actually, when it says interpolated function, it's like a empirical function or a function of like potential data points. So imagine, we didn't specify exactly at what times we wanted the solution, but this is a thing where I can make a plot of data points at any particular time I want. It's basically going to go in there and pick out the times that I want, but it's not a mathematical formula, okay? So it's a little bit confusing, but basically it's a set of data points, okay? In between Tmin and Tmax that describe what the velocity is doing. So this isn't so useful looking at it, obviously. So what I need to do is actually make a plot of these values in order to see what the solution looks like, okay? So that's what I'm going to do here. So let's just go ahead and run this, and then I'll show you what the output looks like. So what this says here is it says, here I've got this stupid, arrow thing here where it says like there's z is arrow, this interpolated function, v is arrow, this interpolated function. This bit right here says both of these interpolation functions, these empirical functions depend on time, so I can evaluate what data points are at a particular time. So again, I'm using slash dot notation to basically extract the data out of this. It says, hey, store in this a new variable called position. I wanted you to basically replace z of t in this rule with the first numerical solution. And so that's just this, the only solution that came out of that there. And then same thing here, but now I want you to replace v of t. So it's not great syntax, but you get used to it, and that's what it does, okay? It becomes more clear when you try to plot it. Okay, so here I'm plotting position and velocity in between 0 and, in this case, I don't even know if that was the maximum time. Less than the maximum time. So I didn't have to go all the way to the maximum time, but I'm going to 4,500 seconds, okay? And you can see here, it looks like a projectile, but the velocity is a little bit different than when we solved for a constant acceleration, and that's, again, because of the change of the acceleration of gravity as this object gets higher, further away from the center of the Earth and reaches its apogee. Okay, and again, we did this with this test case scenario because now it would be quite easy for me to reduce the gravity or something like that and rerun through all this and get a new solution for that particular case. So let's talk a little bit more about working with interpolated functions, okay? So even though it doesn't look like a list of data like what we got out of our MATLAB routines, it kind of is like that, but I just have to tell it where I want it to like extract from this empirical function or this thing, like where do I actually want to know what the velocity is, or what time do I actually want to know where the velocity is, okay? Other things I can do with it is numerically, I can also take, it's not a function that can be described with a mathematical equation, but I can still numerically take the slope or the derivative of this with respect to time. So I can treat it kind of like a regular function, and this is an example of that. So I can take the first derivative of the position and get an expression for the velocity, and it will locate just like this function here. In fact, I can prove that to you. Let me do that. Yep. And then if I want, I can take the second derivative with respect to time and get something new, which is the acceleration, okay? And that looks like this, okay? And again, acceleration is not constant because it goes down with time for our projectile because it's getting further away from the surface of the Earth, or the center of the Earth more accurately. Again, I can do other things similar to what I did in the last example, like try to find the position of this object at a particular time. Here, I am finding the position minus the radius of the Earth at a particular time, because maybe I want to figure out how high this thing is, or the altitude of it relative to the surface of the Earth. So let's just go ahead and run this. Again, you guys might want to spend more time looking at this on your own if you're curious. So I'm using find root, which, if you guys remember our solvers, we had both a solve function that could solve analytical problems, basically do the math or the algebra to figure out what the value x was in some kind of algebraic relationship. Find root was like our numerical method, which we learned about the bisection method and other types of things in class to figure out how to solve these kinds of expressions numerically. So that's what we're doing here. So this is finding the position of this object at a particular time, and it's doing it again in the stupid replacement rule format. And so if I want to extract the actual time, I'm going to use this type of expression. And if I want to find the velocity, I can go back. Remember, velocity looks like that is just another interpolated function. And now I can basically say, in this interpolated function, basically do this replacement rule. So let me write out what solution says again. Okay, so basically in this velocity interpolated function, replace t with the time, which is 4,351, and then that gives me the velocity. So I can go over here and kind of make sure that makes sense. So it's over here somewhere, so it is a big negative velocity. Okay, so again, I recommend you look through here. It's kind of boring to watch me go through it on this video, and there's lots of text here. This is just another example kind of doing the same thing. So now we're looking at the peak height. Okay, so the default here is I'm finding where this expression for velocity is equal to 0. That's going to be true at the apogee, or the peak altitude or peak height of this object. And so I can find the time of the peak height, and then I can do a substitution to find the peak position. Okay, so that's kind of cool. It's kind of powerful.